Well, the goal is usually going to be to have a very short and sweet video, something that gets all the material covered quickly. This is a bit of a review, so because of that, there's actually a lot of things here. You need to know them all. So let's just start off with some definitions and some examples to go with that into your notes. We're going to be simplifying algebraic expressions, which is another word for what's called a polynomial, which we'll look at in a second. Before we discuss a polynomial, we need to know what a term is, because a term comes from the definition of polynomial. So if we don't know what a term is, we can't really define a polynomial. So a term is the product of at least one of the following: constants, variables, radicals, and exponents. So an example of a term would be like this, would be 3. 3 is a term because it's at least one of the following things. It is a constant. A constant is just a number. Whereas another term would be 5x, because that is a combination of 5 and x. Combination, when I say combination, I mean product. These things are being multiplied together. Negative 5x would also be a combination of those things. That's a product of negative 1 and 5 and x. Whereas another example would be negative 5x squared, and that's because that would be the product of negative 1 and 5, x and x. So it's actually x times x. That's why squares and exponents are actually important in defining a term, because the exponent is the amount of times that that variable occurs. So it's the same thing as if we said this. But no one ever writes x times x. We write it as x squared. So we will do that. Okay? Alright. This term would be called, the number here would be called the coefficient. It's another word for the multiple of the term. This is the variable, and this obviously would be the exponent. Now you might have noticed an interesting one that occurs in this definition, which is a radical. This could also be a term. This would be 3 radical 5, where this would actually be also a coefficient, and this would be called the radicand, the number inside of the radical symbol. Okay, so there's some examples of terms, and a term is what makes up polynomials, and there are different types of polynomials. You have monomials, binomials, trinomials, and then we have polynomials. And if you know your prefixes, you'll have heard of a monomial, so that would be a single term like 0. I'm going to change the pen color here. We got 0. Doesn't this work? I gotta move it up. Sorry about that. I'm getting used to this myself. So a single term would be 0, or x, or 3x, or 4x squared is still a single term. Then we have, let's see, 6x to the third, y to the second. That's 6 times x times x times x times y, so it still fits the definition. This would also be a term. We have negative 3x radical x y to the second. That's still a product of a constant term, variables, and a radical. And the radicals actually, in this case, consist of variables, which can happen. We're probably not going to look at that too much. But it's nice to know that it can happen. So a polynomial, or would be a collection of terms connected by plus and minus. So, for example, the classic you'll see a lot is 3x squared plus 2x plus 5. Alright, this is called a second degree polynomial because the highest degree of the exponents is 2 in this case, where if this was actually 3x to the third, x squared plus 5x minus 4, this is now a third degree polynomial, because the highest degree term of the exponents is a 3. Okay? What the degree is could come up, probably won't come up too often, and these are all separate terms, and they're all connected by pluses or minuses. A 2-term polynomial, 3x plus 4, for example, is called a binomial. Bi is the prefix for 2, whereas this is actually a 4-term polynomial, but if we actually erase this one, this is now a trinomial, because it has 3 terms. Let's move on. Okay, so there are 2 types of terms. There are like terms and unlike terms. Now, like terms have the same variables, exponents, and radicands. I'm not going to really focus too much on the radicands, but I do want it as part of the definition, because I don't want to change my story later on. Here are some examples. 0 and 3x squared would be considered unlike terms because they don't have the same variables. Alright, so they go here with unlike terms, and we'll see the importance of knowing the difference later. This is 3x and negative 6x. Now, some people who don't understand what like terms are would assume that these are unlike terms because their numbers are different. But the numbers, the coefficients, the constants, those do not have to be the same in order for them to be like terms. If you look at the definition, terms that have the same variables, exponents, and radicands. They have the same variables, which is x to the first power, so they have the same exponent, which is 1, and they have the same radicands, which is none, or radical 1, which is 1, which is nowhere. So they have the same variables, same exponents, same radicands. These are like terms. Let's take a look at another example. These look like they could be like terms, but they're actually not, and if you're not sure why, part of the definition again, exponents have to be the same, which they are not. This is 6 times x times x times x, whereas this is 16 times x, so they're different. They're unlike terms. Another example we got here. This one's actually a pretty tricky one. They do have the same variables, they have the same exponents, but they don't have the same amount of each variable. So the exponents actually have to be the same for the accurate variable. This is 13xyy, and this is 60xxy. They're actually different, even though they look the same. So these are unlike terms. Okay, and what do we got here? We got 13x to the 5th and minus 5x to the 5th. Again, they have the same variables and the same exponents, so those are actually like terms. And then we have 7 and negative 19. Now, they have the same variables, which is no variable, and they have the same radicands, which are no radicands. So these are like terms. And the importance of like terms, which we'll see shortly, are that you can add them. I'm pretty sure you all know how to add 7 and negative 19, which should be negative 12. Alright, let's move on. So combining like terms is something you can do. It's something you cannot do with unlike terms, and the reason you can do it has to do with what the definition of multiplication is. 3x squared is really the same thing as saying x squared plus x squared plus x squared. That's what 3x squared means. You have x squared 3 times, you add them, they equal 3x. So based on that, 2x squared plus 3x squared should be equal to 5x squared. And that's because this is x squared plus x squared. This is x squared plus x squared plus x squared, which makes a total of 5x squared. Excuse me for leaving out the exponent. So when you have like terms, meaning they have the same exponent, same variable, same radicands, you can actually add their coefficients. So to combine like terms, combine their coefficients. I know my spelling is horrible. If you would like to clarify something with me, let me know in class. First thing you get a chance to. Alright? So combining like terms is necessary for simplifying algebraic expressions. Let's take a look at an example of one now. We have a complicated expression down here. and not all these terms are like terms. We have negative 7x, which is a like term to nothing here. The 3x to the third is a like term to 5x to the third, and the negative 6x squared is a like term to the 9x squared. So there are like terms, they're just not together. And understanding how we can manipulate them is useful also. So we're going to look back at an old property from Algebra 1, and that's called the Commutative Property. It's hard to write a good definition for the commutative property, but I've kind of converted it so it'd be more practical for use in Algebra 2. It says you can switch the order of two signed numbers being added because they will result in the same value either way. Now, the commutative property traditionally looks like this. That's a plus b is equal to b plus a. That's the commutative property of addition. There is also the commutative property of multiplication, which says a times b is equal to b times a, which is also true, but subtraction is not commutative, so you're not actually allowed to switch the order of two terms that are being subtracted. But if you consider them signed terms, like this is negative 6 and this is positive 5, you can switch them. And that is because this is 5 plus minus 6, in which case you can switch the order here. Which says we can actually switch the order of these terms around to help us add them. For example, I want to put the positive 3x together with the positive 5x. I want to put the negative 6x squared together with the positive x squared, and I'll put the negative 7x on the end. Now I can combine the like terms. So 3x to the third plus 5x to the third is equal to 8x to the third. So we only combine the coefficients. A lot of people wind up adding the exponents, which you are not supposed to do, and we'll look at that again soon, so don't do that. We have negative 6x squared plus 9x squared, which has 3 more positives than negatives. That's why it is positive 3x, and the negative 7 has nothing to combine with. I left out the squared. Try not to leave things out and make mistakes. So that would be our final simplified result. Okay. And one last thing to look at, because it's a very old rule again that I'm going to show you, and it's something you should know already, but just in case someone doesn't know this, or maybe taking it down from the video will be more helpful, you can do that. And this should be the last thing on the video. And then we'll get to some classwork. Oops, wrong direction. The distributive property. When multiplying two polynomials, we multiply each term of the first by each term of the second, and then combine them. So this is an example with one monomial and a binomial. Mono meaning 1, bi meaning 2. So we multiply the first term first by each term of the second. So this is going to be multiplied by each term of the second. So that's the first term, and that's the second term. 3 times 6 is the first multiplication, and then we're going to combine them. That's negative, that's 3 times, should have written this the other way. Let me erase this. Okay, so that is 6 times 3 minus 5 times 3, which is the same thing. If you work that out, we'll get here, this is 3 times 1, which is 3. This is 18 minus 15, which is also 3. So it works. The idea is that any number outside the parentheses you can multiply by every number inside the parentheses, which gives us this. And because it works with real numbers, and most things that work with real numbers are also applicable to algebraic expressions, which is why we need to know it. So 3 would also multiply by these. Alright, so 3 times negative 6x to the fourth will become negative 18x to the fourth. And 3 times x, this is actually 1x. There's no coefficient. The coefficient we assume is 1. If it were 0, it wouldn't be there at all. So it has to be a 1. So 3 times 1 would be 3x. And over here we actually have a negative, which really means negative 1, which a lot of people make a mistake of. So negative 1 times 2x to the third is negative 2x to the third, and negative 1 times negative 5x squared is positive 5x squared. Okay, so those are just a bunch of review things that we'll be looking at as we go through the polynomials unit. Thank you very much.